Despite all the derivative rules that we've come up with so far, there are still lots of things that we can't differentiate. Lots of situations where we just don't have enough derivative rules to compute the derivative completely. So here's an example, sine of pi over x. Now, we have a derivative rule for sine, right? We know the derivative of sine is cosine, but this isn't sine of x. This is sine of pi times x. And this pi, that's going to change things somehow, but we don't really know how. Here's another example, square root of 1 minus x squared. Again, we know the derivative of the square root of x. We could just use the power rule, but this isn't the derivative of this function isn't just the square root of x. It's the square root of some other function of x, right? There's this inside function here, and our derivative rule for our power rule for derivatives really only applies if the thing inside the exponent, or the square root in this case, is just the variable x. So our power rule doesn't apply to this situation because the inside is more complicated. Here's yet another example. Now, in principle, if we multiplied out this polynomial, we could just use the power rule, but I would rather not multiply out this polynomial because it would take me all day to raise this thing to the 100th power. And probably I would make some arithmetic mistakes on the way, and then, my result would be wrong anyway. But again, here we have an exponent where the thing inside isn't just x, it's a little more complicated than just x. So this is actually very similar to the situation with square roots. We have a power, which we understand, but the stuff inside it isn't just the variable x. And as a final example, if we wanted a general formula for something like the derivative of f of cosine of x, well, the derivative of f, we'd write that f prime, but it's hard to know how having a cosine inside affects the derivative, right? The derivative of this whole thing isn't just going to be f prime of x. That doesn't make any sense. This cosine inside has to do something to the derivative, but we don't really know how it will affect the derivative. You can see that what unifies all of these examples is that there's kind of an inside function that I'm putting in blue boxes here. There's an inside function that's being put into an outside function. So really, all of these examples, they're just examples of one function inside of another function, right? And we call this operation function composition, right? We can write this, if we have a function g inside of a function f, we sometimes write this as f composed g. That little tiny circle there is pronounced composed with, so f composed g. And right, this is a way of combining functions, just like addition or multiplication is a way of combining functions. We have a derivative rule for addition. We have a derivative rule for multiplication. Maybe we should also have a derivative rule for function composition. Well, as usual, it's hard to come up with a derivative rule if you have no idea what it might be, right? What we've seen in the past is if you have a decent guess for what the appropriate derivative rule is, then it's much easier to prove that your guess is correct than it is to sort of come up with a guess and prove it simultaneously. So before we attempt to actually prove any sort of derivative rule for composition, let's look at an example of a situation where function composition comes up naturally, and we will sort of intuitively ask ourselves about what the derivative of a composition would be in that situation. So here's a situation I have in mind. Suppose we have a weather balloon that's floating up into the air at 5 meters per second, and the air temperature that day changes at a rate of minus 1 over 200 degrees Celsius per meter. Right, as you go upwards, the temperature drops. So this is how quickly the temperature is dropping as you ascend into the atmosphere. What is the rate of change of the temperature that the balloon measures? So to really understand why this is a situation with function composition, maybe we should come up with some names for the functions that are kind of hiding in the background of this context. So We have a weather balloon that's floating up, so its altitude is changing. So let's name the altitude function. Maybe we'll call it a of t. That's a function of time because this altitude is changing as time goes on. So a of t, this will be the altitude after t seconds. And we won't worry about trying to find a formula for this function. It's all we really need is a name for it. So a of t is the altitude after t seconds. So with that in mind, let's interpret this 5 meters per second. Well, that's the rate of change of the altitude with respect to time. So this is dA dt. So that's 5 meters per second. Okay, now what about the air temperature? Well, the air temperature, it changes at a rate of -1/200 degrees Celsius per minute, or I'm sorry, per meter. So since the air temperature depends on how high you are, what we're saying is that the air temperature is actually a function of your altitude. So I guess let's name this air temperature capital T, and it's a function of your altitude. So altitude is A, so T of A. That's the temperature at altitude A. And that's A is in meters here. Okay, and we know that the air temperature is changing at this rate. Well, this is the rate. You can tell just by the units that, right, the unit on top is the unit for T, for temperature, and the unit on bottom, meters, that's our unit for altitude. So this means that this rate, it's a rate of change of T, not with respect to temperature, not with respect to time, but with respect to altitude, right? Because remember, the units for a derivative are the unit for the thing on top, which unit for capital T is degrees Celsius, and divided by the unit for the thing on bottom, and the units for altitude is meters, right? So just by looking at the units, we can tell that this rate of change is actually a value for d capital T dA, so d temperature, d altitude. And this is -1/200, and this is degrees Celsius per meter. Okay, so now let's see if we can answer the question, what is the rate of change of the temperature that the weather balloon measures? It's kind of implicit, so maybe I should have said this explicitly for this setup, but the rate of change I have in mind here is the rate of change with respect to time. So the rate of change of temperature, that would be some sort of derivative of temperature, d capital T. But if we want the rate of change with respect to time, that means this should have a d little t underneath it, right? So the units for this would be degrees Celsius per second, right? And this is the correct unit for a rate of change of the temperature with respect to time. But what is it? Well, sort of intuitively, we have this sense that it's going to somehow be built out of these individual rates of change that we already have. And if you think about the units for this rate of change, 5 meters per second, and this rate of change, degrees Celsius per meter, there should be some way of combining them to produce this unit, degrees Celsius per second. Adding them doesn't make sense, because if you can only add things that have the same units, and these don't have the same units, so subtracting them also doesn't seem to make any sense. But what about multiplying them? If we multiplied these two units, we would multiply meters per second by degrees Celsius per meter, and then the meters would cancel, and we'd end up with degrees Celsius per second. But that's the unit that we were expecting to get. So at least based on units, it seems like maybe the right thing to do here is take our 5 meters per second and multiply it by our -1/200 degrees Celsius per meter. And that would give us, what, I guess, -1/40 degrees Celsius per second. And, you know, that has a certain amount of intuitive appeal to it, because if you're going up at 5 meters per second, but then every meter that you go up, the temperature goes down 1/200 degrees Celsius, then it seems like just multiplying how many meters you go up by the change per meter is the right thing to do. So in addition to getting the units right, this multiplication sort of seems intuitively correct. Now, if we write these rates of change, this one and this one, just using the symbols that we came up with up here, what we get is d capital T, d little t. We think that this is, so 5 meters per second, that was our value for dA d little t. And minus 1 over 200 degrees Celsius per minute, that was our value for d capital T dA. And this also seems to make our guess seem correct, because it seems like, well, look, if you just cancel the dAs, then you get d capital T over little t. Now, you know, that makes this guess seem appealing. This isn't a proof at all, because remember, dA doesn't actually mean anything on its own. dA only makes sense in the context of this clump of symbols, right? This clump of symbols is a derivative. It doesn't make sense to cancel a piece of the symbols. So, you know, what I'm saying is this notation makes this guess of a derivative rule seem correct. It's not a proof that it is correct, but at least it makes it seem correct. It's very suggestive, right? So there's 3 reasons why it seems like this is the correct derivative rule for this situation. So we have temperature as a function of time. It's temperature of altitude of time. So that's why this is a composition. And it seems as if the derivative of t composed with a is the derivative of t with respect to a times the derivative of a with respect to t, little t. Okay, so again, this is just a guess, but it seems like a sensible guess. So now that we have a good guess for what the appropriate derivative rule is for a function composition, now we can get into proving it.